Very good. So thank you for joining us to this AMET seminar. We are very happy to have Aziz with us. Haris, take it away. You know the rules by now. So take it away, 60 minutes plus a few minutes for discussion. If you're new to our seminar, just and you have questions, just unmute yourself and ask the questions. Haris, the floor is yours.
Thanks, JC, and thank you for inviting a computer scientist to an econ seminar. So today I'll be reporting on some joint work with Florian Brandl, and this project started last December when Florian was based at Princeton, and just recently he has joined Bonn. So this is very much a market design / resource allocation project, and the fundamental question that we're looking at is who gets what and why. And we'll consider this question in the context of healthcare rationing. So such an informed audience already knows that market design has had various applications in health. I give a couple of applications. One prominent example where both computer scientists and economists have contributed is that of organ markets, in particular kidney exchange. And an even more classical application is that of matching hospitals to doctors via the famous deferred acceptance Gale-Shapley algorithm. So in this particular project, we'll be focusing on healthcare rationing, as I said earlier, and we'll be focusing on allocation of scarce or costly resources such as ventilators, vaccines, ICU beds, antiviral medicines, and so on. So making these kind of decisions about who should get an ICU bed is termed as one of the hardest questions that doctors may have to face. And the idea behind this particular project is that we want to formulate clearer rules or even a computer algorithm to aid this human decision-making process. Same kind of issue also comes up in vaccine rollouts when people talk about whether a disadvantaged group should get vaccines first, healthcare workers should get it earlier, or perhaps elderly people have the highest priority for getting these vaccines. So a lot of work is done in this regard. So people in medical ethics think quite deeply about this issue, about what are the criteria, what are the principles, and what are the values behind making these allocation decisions. So I'm just giving you one particular example, which is quite local. It's a Sydney Health Ethics Framework, which came out last year. And three prominent values which were mentioned in that report include equal value for all, getting the most out of resources, and giving priority to those in need. So in terms of concrete rules, one concrete rule which is used in certain places around the world is that of quantifying how much a particular person needs a health unit. And by using this quantification, you get a priority ordering based on this Cardinal scale, and using that priority ordering to make allocation decisions in a greedy manner. However, it's been pointed out in several papers that such an approach can be restrictive. It does not take into account various ethical principles, at least very explicitly. And there are various other limitations as well. So I'll mention a few. Some principles do not have a natural Cardinal scale. Secondly, there's an issue of comparing apples with oranges. It might not be possible to aggregate across ethical values, and issues such as explainability or incomparabilities come into play as well. And some principles may depend on the distribution of patients. So depending on which groups have been disadvantaged, you might want to cater that in your allocation making process. So a general widely understood principle which covers many of these frameworks is that you want to take into account various ethical principles. So I quote a Deeble Institute report. Deeble Institute is from Australia, and I've been communicating a bit with them as well. So there's a nice quote which says that we need to acknowledge the various implicit and explicit priorities that influence the process and develop a decision-making tool that incorporates them. So in terms of priority groups, people have been looking at quite closely at the COVID vaccine rollout. So it's pretty clear that there are some groups which are viewed as more important than others. So I'll give 3 examples of priority groups, which are mentioned in many of these frameworks and reports. So governments may want to prioritize healthcare workers. They may want to prioritize elderly people, and they may also want to prioritize people who are more vulnerable to a certain disease, or they more urgently need healthcare. So the general question that we're looking at here is, how do we allocate scarce medical resources fairly and efficiently while taking into account various ethical principles and priority groups? So we're not the first to look at this particular question from the context of market design. So last year, a very prominent paper came out. In fact, there's even an AMET's presentation on this later part of 2020. And this is a paper by people most of you would recognize, the very prominent market designers, Parag Pathak, Stefan Sonmez, Utku Anwar, and Yenmez. And this paper looked at fair allocation of healthcare resources. And one part of the title, in fact, explicitly states that we don't want to leave out any ethical values behind in healthcare rationing. So let me just go over the very basic version of the model considered by these market designers. They've came up with a very general model, which not only applies to healthcare rationing, it also applies to many other rationing problems. So there's a set of agents. We just use a general term agents rather than patients because this model applies to many contexts. There's a set of categories denoted by capital C, and each category C, small c, has QC units, and all of these units are healthcare units which are identical. There's also another bit of information in this input, which is that each category has a priority ordering over agents, and this priority ordering compares which agent is more higher priority than another, and it also specifies which agents are eligible for that particular category. So this model will become clearer with this simple example. This is an example where you have 3 agents on the left side. These are the patients who want to use one of the units. And let's say in this case, you have 2 categories, C1 and C2, and each of these 2 categories has exactly 1 unit of healthcare resource. Both of these categories also has their own priority list. So C1 has a priority list which has the highest priority for 2, then 3, and lastly, it has priority for agent 1. And in the middle, you might see this empty set notation, which simply signifies that agent 1 is ineligible for this particular category C1, whereas agents 2 and 3 are eligible for category C1. Similarly, you have a similar priority list for category C2. So the approach taken by Pathak et al. Was that they took a very matching based approach where there are agents on one side, you have categories on the other side, and there's a natural eligibility reservation graph where you have an edge from an agent to a category if that particular agent is eligible for that particular category. So based on this formulation, you can find a matching, and that matching might be a reasonable outcome for this particular problem. So this work by Pathak et al. Has caught on quite a bit. There's even a dedicated website for their work as well as follow-up work. So this particular website, if you're interested, it also keeps track of policy impact, and it also keeps track of further research in this area. So this problem got a lot of media attention as well, with articles in New York Times and so on. So when this work came out, some of the ideas behind this work also made it to the North American Framework for Equitable Allocation for COVID Vaccine. And I'll go into a few ideas behind in this paper, but in particular, I'll mention a couple of rules which are in this paper. So the first approach of Pathak et al. Was based on viewing this matching framework and then thinking in terms of applying a deferred acceptance algorithm for this problem. If you recall the deferred acceptance formulation, it typically assumes that both sides have strict preferences and priorities over the other side. So in this case, one can artificially break the preferences of agents over categories. And after that, one can directly implement the deferred acceptance algorithm. And if you do so, what Pathak et al. Showed was that the outcomes are characterized by three very nice, simple axioms, which are not only meaningful in the matching market context, but they're also widely received and recognized in the ethical healthcare circles as well. So if you do allocation in this way via deferred acceptance, then you get a matching which complies with eligibility requirements, which simply means that a patient or an agent gets a unit from a category that particular agent is eligible for. Secondly, the outcome respects priorities of the categories, which means that you do not have a situation in the figure in the middle of the page where you have agent I who is unmatched, agent J is matched to category C, but it turns out that category C has a higher priority for agent I over agent J. So you don't want to have this kind of situation. And by using the deferred acceptance formulation, you achieve a property called respect of priorities of categories. And finally, you satisfy an axiom which is very basic and well established in matching theory as well as resource allocation, which is non-wastefulness. So you never have a unit which is unused but could have been used by some eligible patient. So this was the first rule which was present in the paper by Pathak et al. But they also came up with another rule which they refer to as the smart reserves rule. And the reason why this rule is called smart reserves is that it smartly makes choices about which category an agent should utilize in order to make sure that the outcome is a maximum size allocation. And by maximum size allocation, I simply mean the maximum size matching, which allocates the largest feasible number of units to patients who are eligible for categories pertaining to the units. One assumption that this particular rule makes is that it's based on the assumption that all categories have homogeneous or consistent priorities. One nice thing about this rule is that it interpolates between two extreme interpretations of reserves. And this thing I will go into much more detail a bit later. So just to summarize, in terms of just looking at the rules in the paper by Pathak et al., there were two prominent rules. One is the application of deferred acceptance by breaking ties, and another is the formulation called the smart reserves rule, and it has its own relative merit. So whereas the deferred acceptance rule can handle all kinds of priorities, even heterogeneous priorities, the deferred acceptance formulation has a disadvantage that it does not give an outcome which is maximum size matching. On the other hand, smart reserves rule, it does not handle heterogeneous priorities, but it does find a matching which is maximum size. So the starting point of this particular project was an observation that you have these two nice rules. Can we get a rule which sort of achieves all the nice properties that are in this table and also some other properties that I will describe? So the main research question that we have here is that how do we tackle the same problem, but when we have the case of heterogeneous priorities? So coming back to one example, let me just motivate an example which concerns heterogeneous priorities. If you have heterogeneous priorities and you use a deferred acceptance algorithm, then we can artificially break ties. So the agents can have artificial preferences over, let's say, each agent prefers category C1 over C2. And based on that, you can then run the deferred acceptance algorithm. But it turns out in that case that agent 2 is matched to C1 and that is it. So it does not find another matching, which is actually maximum size, which is this matching in blue. And what we want to do is we want to find a matching which is maximum size. And it also is a matching which satisfies other nice properties such as respect of priorities. So in terms of challenges, one challenge is that artificially inducing preferences, as we saw in the previous example, it can lead to globally suboptimal outcomes, especially in terms of finding maximum size matchings. Another thing that we note is that if we introduce preferences artificially, so that you get strict preferences or strict priorities on both sides, then in fact, it's a well-known result in computer science that it's an NP-hard problem to simply find the maximum size matching which is stable. Those of you who work in matching markets, you might have observed quite quickly that respect of priorities is quite close to this aspect of justified MV freeness. And finally, there's also an aspect of strategy proofness, which if not that important here, it can be important in many reserve system problems, especially when you are giving health rationing school seats or various other applications. So what do I mean by strategy proofness in this context? Since agents are simply indifferent among all categories or units of all categories, well, agents may have some incentive to either lower their priority in a category. This could be the case if not in healthcare, it can be the case in school choice. And agents can also have some option of hiding eligibility of some categories. So ideally, we want a rule which does not incentivize agents to misreport any of this information. A weaker form of strategy proofness that we consider here is called privilege monotonicity. It was already considered in a paper by Igon and Bo, and that is a restricted form of strategy proofness which does not incentivize agents to hide their eligibility. Privilege monotonicity can also be viewed as a sort of fairness property, because agents who become eligible for additional categories, they should not be harmed by this additional eligibility. So let me just summarize our contributions. So firstly, we show that there exists a rule. In fact, I'll show there exist two rules. One of them is called the reverse rejecting rule that complies with eligibility requirements. It respects priorities of categories. It yields the maximum size matching. It is also non-wastefulness. It also is non-wasteful. In fact, maximum size matching implies non-wastefulness, but I've explicitly mentioned this property as well. The fifth axiom that is satisfied by our rules is strategy proofness. And finally, we show that this can be done in polynomial time. After that, I'll explain how our rule, the reverse rejecting rule, can actually be extended to a more general class of rules called smart rev, in which a given number of unreserved units are processed earlier and some unreserved units are processed later. So I'll discuss this aspect a bit later. What we note here is that a general class of rules, it generalizes two well-known reserve rules, over and above and minimum guarantees, that are two extreme interpretations of reserve rules in all these category systems. And finally, one contribution we have is that we also provide axiomatic characterizations of these classical over and above and minimum guarantees rules. And we'll discuss how our rules also, and all their properties, they also work as well for what is called soft reservations. All right, so before I proceed and discuss our own rules, let me just mention a few pieces of related work. This is just a representative sampling. There are lots of papers which can be seen in our reference list. So in terms of related work, this work is quite close in spirit to matching with diversity goals, which is often used in school choice. And in there, typically the diversity goals are specified in the case of minimum and maximum quotas. So there are a few papers here. In particular, one of the earliest ones is by Abdul Qadiroglu in 2005. There are also some works which use either sequential or some kind of iterative greedy process of treatment of categories, and there are quite a few papers which use that. The third bullet point actually is probably the closest to our problem. In fact, the models are quite similar. So the first paper is the one which inspired this paper, the paper by Pathak et al. There's another paper by David, who also presented at AMET. So in fact, I've highlighted the two papers which have been presented on a very similar model, and in fact, they were presented in AMET's seminar last year. And finally, this work is also related more generally to matching with distribution constraints. So before I go into our rules, let me mention one thing which we use, which is also used in some of the previous papers, and that is the use of a baseline ordering. So baseline ordering is an ordering over agents that is used by our algorithms. It could just be a randomly generated ordering, or an alternative interpretation for this baseline ordering is that it's a priority list over the general public. Note here that this baseline ordering does not override the priorities of the particular categories. So this will not overbear on our results, because it's only used to make certain decisions to come with an outcome for our particular rules. So the first rule that I want to mention, that I actually did not mention in the contribution, but it's mentioned here for historical purposes because, in fact, this is the first rule that we came up with. And in fact, we put up an archive report based on this particular rule. So this is called the weighted reservation graph rule. And what it does is that it takes the underlying eligibility or reservation graph where you have agents on one side, you have categories on the other side, and the edges simply signify the eligibility requirement of an agent for a particular category. So that's the edge set. But this particular bipartite graph is not just based on the eligibility relation, it's actually a weighted graph. And the way we set up the weights is as follows. So if you have an edge which is I comma C, for that particular edge, we have a weight which is written as follows. So it has a component which is 1, which is whenever you have an edge, you give that particular edge a component weight of 1. Then it also has an additional component which is responsive to where exactly is that agent I in the priority list of category C. So WCI comma C is n minus L times epsilon, where epsilon is some small value, where and L is the Lth equivalence loss of agent I in C's priority list. And finally, we perturb this particular weight slightly by adding an additional bonus, which depends on the position of agent I in the baseline ordering. So basically what we're doing is we're taking this graph, we are setting up the weights in an appropriate manner. And this weight setting is based on 3 levels of optimization. Firstly, you care about whether that edge is matched or not. Secondly, you care about whether how high the agent is in the priority list of the category C. And finally, you also care a little bit about where exactly is agent I in the baseline ordering.
So, Harris, can I ask you a clarifying question? So on both the priority list in each category and the ordering of agents, these are all public information. So everyone knows that those orderings are there.
Yeah, you can assume it's public information.
Okay.
So based on this information, you can form a bipartite weighted graph. And this is an example from the previous running instance. So you've set up the weights, and all you do is you find a maximum weight matching. And this is essentially our rule. So it's called the weighted reservation graph rule. And it's fairly straightforward to see that it satisfies the eligibility requirements by making or prioritizing the weight of 1 as the highest weight among all considerations. We also make sure that it's a maximum size matching. And by making sure that we are responsive to the priorities of the categories, we also achieve respective priorities. What did require a fair amount of work is establishing strategy proofness for this particular rule. But otherwise, it's a very simple rule. All you do is you set up a graph, a corresponding weighted graph, and find a maximum weight matching for that particular graph. So
Harris, I'm sorry to interrupt again. So I still have a question regarding strategy proofness. So you mentioned that you are assuming arbitrarily a preference for each agent. So
it's not really a preference. So we say that in basically agent is indifferent among all units of all the categories. So what exactly can agent misreport? We assume that agent has the power to do the following. It can make itself ineligible for a certain category by not making it publicly known or not reporting that it's eligible for that particular category. We want the rule to not have an incentive for agents to underreport or hide their eligibility. But the way we have defined strategic proofness is a bit stronger. We even allow agents to lower their priority in the priority list of some category. And this can be the case in other application contexts. For example, if you consider a school choice context, there might be different categories, let's say category for sports scholarships, or it could be category for academic performers. And you do not want students to underreport or underperform slightly in any of these categories to get an advantage. That's a very natural requirement, that you want people to perform to the best of their ability rather than underperform in certain categories. So that's what's capturing strategy proofness.
Thanks.
Yeah.
Could you please back on the example, the graph example?
Yeah.
And could you say why the third age is 1 plus epsilon? I want to understand how you build this graph, and the first age is 1 plus 2 epsilon.
So 1 is for every edge. Why is this agent 3 having a contribution of epsilon rather than 2 epsilon is because you have 3 agents. So if you see n minus L times epsilon, you have 3 agents, and agent 3 is in, let me just go back a bit. Agent 3 was pretty low in the category, right? It was pretty low in C1. It's second in the place. So for that reason, it's getting an epsilon rather than 2 epsilon.
Okay, what is L in this?
N is the number of agents.
Yeah, L.
Yes, N is the number of agents. Let me just go back. N is the number of agents, and L is the position of the agent in the priority list of the category.
Okay, thank you.
All right.
Yes.
Any other questions before I proceed? Okay, so this is in fact not the main rule that I want to go into more detail, but this was our first formulation, or the first thing we came up with, and it did a good job, because if you compare it with the previous rules, it does handle heterogeneous priorities, it does comply with eligibility requirements, respective priorities, and so on, and it also satisfies the strategy proofness requirement. However, it relies on finding maximum weight matching, so maybe we want a rule which is computationally even more efficient. Secondly, this particular rule, it does not characterize outcomes with respect to these properties. It only finds a subset of these properties. So what we did was we went for another rule, which is in our paper, which is now the central part of our paper. And that particular rule is called the reverse rejecting rule. So in contrast to simultaneously selecting agents or iteratively selecting agents, this rule has a very different methodology. So what it does is it does use the baseline ordering, but then it goes in the reverse direction of the baseline ordering. And rather than selecting agents, it tries to remove agents and add them to the rejection set. And we only reject agents if we can do so while satisfying certain conditions, which will become clear when I give you an example. In particular, we say that we stop when we can't reject anymore without compromising on the maximum size property which we want to achieve. So this is the pseudocode for this particular rule, but since this is very much a computer science centric view of formulating a rule, I think it'll be easier if I give you an example to show how this particular rule works. So what we do is we'll start with a problem instance which has 4 agents, 1, 2, 3, 4. We have 2 categories, C1 and C2, and each of these categories has a capacity of 1. The priorities are as follows: 1, 4, and 2 for category C1, and for category C2, the highest priority is agent 1 and then agent 3. So let us simulate the reverse rejecting rule on this particular instance while using the baseline ordering of 1, 2, 3, 4. So what we do here is that we start with an eligibility graph, the underlying eligibility reservation graph, which is agents on one side, categories on the other side, and an edge signifying the eligibility requirement. After that, what we will do is we will keep on modifying this graph by deleting agents. And if we can delete an agent, we will delete so. Under certain circumstances, we will decide not to delete an agent. So what we do is, since the baseline ordering is 1, 2, 3, 4, the first agent that we try to delete is agent 4. So we try to delete agent 4. And when we delete agent 4, we are also required to delete certain other edges. And the reason for deleting certain other edges is because we want to respect priorities of categories. For example, here, when the moment agent 4 was removed, we also removed the edge from 2 to C1. And the reason for this is because agent 2 is actually lower than agent 4 in the priority list of category C1. So for that reason, you might see this edge, which was previously going from 2 to C1, but now it has been removed. At this point, what we do is we check whether a maximum size matching of this graph can still be computed while we have removed from consideration agent 4. And since we know that the maximum size of this matching is 2, we can still find a maximum size matching of size 2. So we have successfully removed agent 4 from consideration. The next candidate for removal is agent 3, because agent 3 comes after agent 4 when we go in the reverse ordering. So we try to remove agent 3, but it turns out that the moment we remove agent 3, we cannot get this maximum size matching property anymore. And for that reason, we reinsert agent 3 and try to delete agent 2. And agent 2 can be removed because if you remove agent 2, you can still get a maximum size matching. And at this point, we don't change the graph further, and we simply find a maximum size matching of this modified eligibility graph, which has had a few edges and a few vertices removed. So at this point, for example, any 1 match to C1 and 3 match to C2 is in fact the unique outcome of this particular rule. So the reverse rejecting rule has some nice properties. It terminates with a feasible matching. It complies with eligibility requirements. It finds a maximum size matching as well. It respects priorities. We prove that it's strategy proof. And since it's simply using as an oracle, an algorithm to compute a maximum size matching, it also can be implemented in polynomial time. So just to summarize, just like WRG, REV does a similar job as well. It satisfies nice properties. But one nice aspect of the reverse rejecting rule is that in fact, its outcomes characterize 3 main properties that have been considered by Pathak et al. So the main theorem is that a matching satisfies 1, compliance of eligibility requirements, 2, maximum size among feasible matchings, and 3, which is respective priorities, if and only if it is a possible outcome of the reverse rejecting rule with respect to some baseline ordering.
I have a good question.
Yeah.
So I mean, it seems a nice rule, except for one property, which is that this ordering favors agents. So here you removed agent 4 first. Agent 1, which is at the top of that ordering, seems to be getting a preference, a priority in this matching, because they're last.
Well, you have, unless you go for probabilistic allocations, you do need to break ties in some way to get a deterministic rule. For that reason, we are using it. But this, as I said earlier, this particular baseline ordering is one of the last considerations. It does not override the priorities that the categories have for agents. So let's say agent 4 really was a higher priority agent for many of the categories, then that particular aspect will not be overridden by agent 1 coming earlier than agent 4. Agent 4 will get selected if agent 4 is high enough in categories of various categories. I hope that answers your question.
Well, it seems to me it's more than just tie breaking. Anyway.
Well, it is not. I'll mention 2 things. So firstly, baseline ordering, if you view it uniformly at random, then it's from an ex-ante perspective, it does not bias against anyone. And the other interpretation that I have for real world applications is that the baseline ordering is in fact a priority ordering over the general public. So it could be priority ordering over the general public with respect to a certain quantitative measure. Based on that, it's not some arbitrary method which is biasing one agent over another. You could still use some principled rule, which is a priority ordering over the general public to make these decisions. But even if you don't do so, this baseline ordering is not overriding the priority or the respective priority consideration that we have for various categories. All good? Okay, so I have a footnote in this particular slide, and that is that even for consistent preferences, there is no such characterization of existing rules. So this is really not just an extension of a previous model. In fact, it's a characterization which is also new, even if we restrict our attention to homogeneous priorities where, let's say, all categories have may have different eligibility sets, but they all have consistent priorities over the agent sets. So for that reason, it seems as if Rev is a nice rule because it captures all three of the key axioms that we are after. One disadvantage that we did notice for the reverse rejecting rule is that it's a rule which is bossy in nature. So even if an agent is not selected by an agent changing the eligibility requirement or its eligibility for a particular category, it can affect which other agents are selected. And this is somehow quite closely related with an impossibility result by Fujito Kojima, which is in the context of stable matchings and non-bossiness. He showed that non-bossiness and stability in general are incompatible, and similar kind of phenomena is also holding in our context, which is a bit different because one side is indifferent among all units of the same categories. The same example can also be shown to prove that this particular rule, if it's just used as a choice set to select which agents are selected, then substitutability is not satisfied. At least when the priorities are heterogeneous, substitutability is satisfied if you have homogeneous priorities. So up till now, I have just considered a set of categories. I have not really distinguished between categories, but just as Toby said that why are we using this baseline ordering? Well, this baseline ordering in many of these real life situations is actually a priority ordering, which is in fact over the general public. So in the context of healthcare, the baseline ordering could be the need for an agent or a patient to get a unit. In other reserve contexts, it also has very natural interpretations as well. So in the school choice application, the baseline ordering could be the merit ranking of students. So the baseline ordering could be based on what the merit scores are in the entrance exam, but you could also have other priority orderings based on different categories, such as consideration to extracurricular activities, or consideration for disadvantaged groups, and so on. So from now on, in this part of the paper, we actually treat these unreserved units or this general public as in an asymmetric manner. So we will distinguish between a category which is called the unreserved category, which is CU, and a subset of categories which is called capital CP, which is the set of preferential categories. And these preferential categories could be particular categories such as giving priority to people from healthcare or frontline workers or people from old age groups and so on. So how do we treat these asymmetrically is done as follows. So firstly, for the unreserved category, we will assume that that unreserved category has the same priority ordering as the baseline ordering, or alternatively, the baseline ordering is the same as what the priority ordering we have for the unreserved category. And secondly, the way we are using it asymmetrically is that now we also have the consideration that we have this axiom called the maximum beneficiary assignment property, which is not about finding a matching which is of maximum size. It in fact also ensures that the maximum number of units are used from this subset of categories called the set of preferential categories, which is CP. Note here that the unreserved category allows for all agents being eligible for that category. It's a general public category. So for that reason, the moment you satisfy maximum beneficiary assignment and non-wastefulness, you also get, as an implication, you get a maximum size matching. So one reason why the unreserved categories are used in particular ways is that in very classical applications, such as giving public jobs to bureaucrats in India, these treatment of unreserved category, whether it's used first or it's used later, can have a big effect on how disadvantaged groups are impacted. So here what we did was, this is our take on a formal approach to specifying these two rules. in the context of the classical applications where each agent is eligible for at most one category, at most one preferential category, and you have homogeneous priorities. So I won't go into these technical details for this, but the main idea is that historically, reserve systems have used unreserved category in two different ways. One is that it treats unreserved units later. That particular rule is called the minimum guarantee rule, and yet another one is called over and above rule, which treats unreserved units first. And whether you use these unreserved units first or you use them later can have a big impact. And this is already discussed in the paper by Pathak et al. And a few other economics papers. And when I did my literature review with Florian on this, what we saw is that, in fact, there are even books from 1961 written by legal professors. So Mark Galanter is one of them, who was an expert on Indian constitution. He was a Fulbright scholar based in India for some years. And he already noticed that this minimum guarantee and over above can have very different impacts on disadvantaged groups. So I give a couple of quotes that minimum guarantees ensures the amount of effective reservation somehow commensurate with the backwardness that inspired it, whereas the minimum guarantees also may overstate the effective amount of reservation in terms of perception. So to make this thing clearer, let me just give you an example. So this is an example where you have 4 agents. You only have one preferential category, which is category C. You also have an unreserved category, which is CU. Each of these categories has a capacity of 1. And what you note is that only the agents in blue, these minority agents, say, or high priority agents, agent 1 and 4, are eligible for this preferential category C. So how you treat the unreserved category first or later can have a big impact, and this is shown in the next slide. So if you go for this minimum guarantees rule, then the matching that you get is 1, C and 2, CU. So agent 1 and 2 are matched. Whereas if you use the over and above rule, then both the two minority groups agents, agent 1 and 4, are both matched. So in that sense, you can say that over and above is more responsive to preferential groups or minority groups, because what it does is that first, it lets them get a bite from among the units reserved for the general public, the unreserved category. And after that is done, they still have an opportunity to those particular units that are solely reserved for them because they are eligible for that particular category. So in that sense, over and above is one extreme interpretation of treating reserves, and minimum guarantees is another one. So what we did is that we took this to a formal approach in terms of coming up with axioms. And what we did was that we divided this unreserved category into 2 different subcategories, which is CU1 and CU2. The number of unreserved categories QCU is equal to QCU1 plus QCU2. And basically what we're doing is we're trying to treat some unreserved units earlier and some unreserved units later to capture this flexibility that is achieved between these 2 extreme rules. So we came up with an axiom which has not been defined in previous work, because typically people talk about rules rather than axioms of outcomes. So we came up with an axiom which is an axiom of matchings or outcomes, and the property is called order preservation. And it requires that no 2 agents should be able to swap their matches so that the eligibility requirement is not violated. And an earlier category gets a higher priority agent after the swap. So this is the main axiom that we use. And it turns out that this axiom is enough to give us some characterization results. So this is the formal definition, which I will not go into detail, but this particular slide already captures the main idea behind this axiom called order preservation. So coming back to these 2 classical rules and the context, which is very restricted, it's homogeneous or consistent priorities of preferential categories. and each agent being eligible for at most one preferential category. These are standard assumptions which are used in some of the classical rules in reserve systems. By doing so, we focus on the first rule, which is called the minimum guarantee rule under this basic context. And what we show is that the outcome is an outcome of minimum guarantee if and only if it satisfies these five axioms listed on the page, which is compliance of eligibility requirements, maximal beneficial assignment, respect of priorities, non-wastefulness, and order preservation with respect to the condition that you have QCU1 equal to 0 and QCU2 equal to QCU, which essentially means that you are using all the unreserved units later. We get a similar kind of mirroring characterization result for the case of over and above. The only difference now is that the order preservation is with respect to a different configuration, where all the unreserved units are required to be processed as early as possible. So these were two characterization results which are for classical rules under very basic context. But what we are after now are general rules where we relax this requirement that categories have homogeneous priorities. We also relax this requirement that agents are only eligible for at most one preferential category. We allow for agents to be eligible for any number of preferential categories. And the idea behind this treating some unreserved units earlier and treating some unreserved units later was already present in the paper Bipartite et al. And it's really one of the nicest results in the paper Bipartite et al. Because it captures two extreme interpretations of reserve rules under very restricted circumstances. It generalizes it to an umbrella of rules where not only are agents allowed to be eligible for multiple categories, but eligibility relations could be different as well. However, this particular rule still assumes that baseline order consistent priorities are used. The nice thing is that it interpolates between minimum guarantees and over and above. What we do now is that we use our reverse rejecting rule as an oracle to come up with a more flexible class of rules, which even generalizes this framework of Pathak et al., which already captures two extreme interpretations, which are minimum guarantees and over and above. So this is the algorithmic formulation of this more general class of rules, which basically is parameterized by how many QC1 units are to be processed earlier, how many units are required to be processed in the end, and in the middle, when you're allocating the preferential categories, you need to do it in a principled way as well. So let me just summarize this algorithm by a few high-level points. Basically, what we do is we go down the baseline ordering, and we try to allocate units from CU1 to agents while ensuring that the maximum beneficiary assignment can still be achieved. So this is what we're trying to do in the previous algorithm. Once the match of CU1 is fixed, what we do is for the remaining agents, we call the reverse rejecting rule on the remaining agents who are not yet matched and the categories which are preferential categories to match agents to the preferential categories. If there are still some agents who are unmatched, they are then allocated units from CU2 to these unmatched agents. And this concludes the process, and we come up with an outcome of this more flexible rule called the smart reverse rejecting rule, which is abbreviated as smart rev. So in terms of properties satisfied, the smart rev rule, it satisfies all the nice properties which we had for reverse rejecting rule, but it also satisfies these two properties which are highlighted in yellow. In particular, it finds a matching which is maximum beneficiary assignment, and it also satisfies order preservation. Note that the reverse rejecting rule, it does not necessarily find a maximum beneficiary assignment, and that is simply because it's oblivious to whether a category is a preferential category or it's an unreserved category. It does not distinguish between these classes of categories. On the other hand, smart rev rule, it does distinguish between the preferential categories and the unreserved category. And for that reason, it satisfies these two properties in yellow. So I haven't really gone into ideas behind some proofs, but let me just give you a very high level idea of why this particular rule is strategy proof. Most of the cleverness.
Harris, can I ask you something, just clarifying question? So for this smart ref, so CU1 and CU2, are those, so the algorithm also decides, what is going to be, how it's going to be partitioned, the CU set?
Yeah, so you can view it as the policy designer making a decision on whether to go for this over and above approach, which is treating all unreserved categories at the end. All unreserved units in the beginning, or the minimum guarantee, which means that all unreserved units at the end, or something in between. So it gives a designer more flexibility in terms of how exactly to interpret the quotas and the reservations, and use that flexibility to see what exactly they want to achieve.
Right.
So it's just giving them more flexibility.
Okay. And when you say it's the algorithm is polynomially, so it's computationally feasible in polynomial time, that also includes the decision of whether you're going to have CU1 and CU2 in a certain partition.
Yeah, so we, as an input, we are just simply assuming that certain number of units are in CU1, certain number of units are in CU2.
And does it matter? No, because all the units are the same, right?
It matters a lot to the agents, how many units are in CU1 and how many units are in CU2. As I showed in this very basic example, whether you treated
right, it changes the location.
Earlier or later, it affected on how many of the disadvantaged or the highly preferential people got. For example, in one of the rules, over and above, 1 and 4 got selected, and the other one, 1 and 2 got selected. So it matters for the agents. It matters for certain preferential groups as well.
Now, the construction wouldn't work if you have different, so heterogeneous items in each category, right?
Yeah, so the whole paper assumes that all units are homogeneous, yes.
Okay. Thanks.
Things become much more complicated. We have a separate paper in the context of school choice where certain school seats are treated differently, and that really leads to a lot of negative results. So coming back to where I was, so I just wanted to say a few things about strategy proofness. So most of the strategy proofness argument is embedded in the fact that the rev rule itself is strategy proof, which I did not go into detail at all. But overall, let me just sketch why this is strategy proof. Firstly, what we show is that whether if an agent is not matched, if an agent lessens its priority in some category or makes itself ineligible, that has no effect on the match of the first unreserved category CU1. That's the first observation we had, or we established that. Secondly, just because the rev rule, which is called in the smart rev algorithm, is strategy proof, by that fact, we know that an agent cannot be matched to any preferential category by misreporting. Finally, an agent, since in this rev rule is bossy, an agent, even if it's not matched, it can affect which agents are matched and which agents are not matched. But what we do show is that an agent cannot affect the number of agents. It can affect the set of agents, but it cannot affect the number of agents with higher baseline order priority who are not matched to CP. And because of this fact, we get that an agent also cannot misreport to get some unit in CU2, the last unreserved category. So this is just a very high level sketch of why the smart rev rule is strategy proof, and most of the argument is embedded in the fact that the rev rule is strategy proof, which I did not go into detail. So in terms of properties, this is just a more comprehensive comparison between smart rev and rev. We see that smart rev is essentially satisfying all the axioms that we have considered in this particular work, in this particular project. Rev rule has some disadvantages simply because it's oblivious to whether a category is a preferential category or it's an unreserved category. Otherwise, we do establish an advantage of using smart reserves rule, smart rev rule, in contrast to certain other rules which have been presented by us as well as some other presented in previous papers. So to conclude, we came up with, people have been looking at abstract rules, not abstract rules, but abstract principles on how to make allocation decisions in ethics circles for a number of years. But Pathak et al., they very nicely connected a very well-established piece of market design, which is matching market design, with this literature on healthcare rationing. And we basically pursue that direction further, and we come up with 2 new rules, in fact, 3 new rules for this problem. So we presented various algorithms for healthcare rationing. We also presented a few characterization results. And in terms of characterization results, I really want to highlight the characterization result of the rev rule, which characterizes 3 main properties which the authors of Pathak et al. Were after. Up till now, I have assumed that the outcomes satisfy eligibility requirements, but in certain contexts, you do not want to have a case where, let's say, a vaccine was dedicated for a certain group of people. All those people have been served, and there is some person who would rather get that vaccine, and that person is not eligible for that particular category. For that reason, in matching markets, especially in school choice, people also use what is referred to as soft reserves. And soft reserve simply means that we relax this eligibility requirement by even allowing people who are not eligible to get a unit from a category if all other people who were originally eligible have already taken their. So all of our arguments, including strategic proofness, they do extend for soft reserves as well. So in that sense, you can get an even better efficiency by using soft reserves if you want to relax the hard reserves requirement. And finally, I want to mention that this paper was mostly written in the language, at least the intro was mostly motivated by healthcare rationing, but it's essentially any kind of problem where you have different categories. Each of these categories may have their own priorities. You could use that for various applications. So one application that is quite prominent in AI is that of algorithmic hiring. You basically use a machine learning algorithm to have a linear ordering over which employee might be most productive in a company, and they use this via some standardized tests to select certain employees. But if you also want to check that this outcome is balanced or it has some affirmative action concerns ex post, then you can simply use that base machine learning outcome as the baseline ordering, but address fairness concerns ex post by using this framework of categories with their own priorities. Similar kind of thing can be used in immigration and school choice. In fact, there are a few papers on immigration already, and many papers on school choice which concern allocation under affirmative action concerns. It can also be used for allocation of marathon, race sports, public viewing sports, and since recently I was asked to serve on jury duty, maybe it can also be used for jury duty exemptions. And this concludes my presentation. I'm happy to take questions.
So before going to the questions, let's thank Harris for this wonderful presentation. And so I'm gonna continue in common practice. I'm gonna stop the recording now.